Hello everybody, welcome back. Today in this video we'll be discussing about the p block elements. Fine. For class 11 we'll be just discussing about the group 13 and group 14 elements, that is boron family and carbon family. Fine, let us proceed with it. So the p block elements are basically elements from the group 13 to group 18, right? So that is group 13, 14, 15, 16, 17 and 18. All the elements which comes under this group form the p block elements, right? And the elements of a particular group are named after the first element in that group. Fine. For example, in group 13, boron is the first element and all the elements of the group are just classified as boron family. Fine. And in case of group 14, carbon is the first element and hence we call it carbon family. In case of group 15, nitrogen family, then comes oxygen family. But in case of group 17, we call all of them as halogens. Fine. And in case of group 18, all of them are inert, right? They are noble gases. Fine. This is how the p block elements are all named. That is usually grouped and classified. Fine. And we know that p block elements are usually non-metals, right? And the non-metallic character decreases as we go down the group. And p block elements is the only group of elements in the periodic table which have metals and non-metals as well. Fine. And the electronic configuration of all these p block elements is ns2 and np1 to 6. Fine. So for boron family it will have np1, then comes 2, 3, 4, 5 and group 18 will have np6. That is the complete configuration. Hence they are inert and they are noble gases. Fine. And we see that in case of p block elements the electronegativity will be high, right? And the ionization enthalpy will also be high, hence they form anions. In case of metal we saw that they form cations, right? And they have low ionization enthalpy, etc. But in case of p block elements they form anions. Fine. And we also know that they have different variety of properties. For example, carbon we discussed in the other chapters as well. Carbon forms multiple pi bonds with itself and with the elements of the next group, that is nitrogen, oxygen, etc. That is the first group, first period of elements. Fine. So they have variety of properties and we'll be discussing about all of that. Basically boron family and carbon family in this videos. Fine. So next, starting with the boron family, it is of the elements of group 13 are named boron family, and these elements are boron, aluminium, gallium, indium and thallium. And when we look at the electronic configuration, we note that from gallium, the t block, that is the d orbitals are also involved. Fine. From gallium, indium and thallium, all these have d block and thallium has s block as well. Fine. F orbitals as well. Fine. So all these elements show a wide variation in properties. Fine. Because yeah, we can see it easily, right? After like gallium, indium and thallium, they have d orbitals and f orbitals involved in them. So the properties will differ anyway, right? Because when we were discussing about the periodicity and transient periodicity, we discussed that when there are, in case of higher elements, when they have d orbitals and f orbitals, they are affected by what is known as screening effect, right? So yeah, that plays a major role in this case. And in all these cases, boron is typically non-metal. Fine. Aluminium is a metal, but it shows some similarities with boron. Fine. And all the other elements, gallium, indium and thallium, are all mostly metallic in character. Hence, only boron is the non-metal in this case, and all the others are all metallic in character. Fine. And yeah, boron has two isotopes. It has two isotopic forms. One is B10 and the other one is B11. And usually B11 is more abundant, that is around 80%, and it's more stable also. Fine. And these are about the isotopes of boron and the occurrence of elements. How is boron occurred? What's the occurrence of boron? Boron appears in the form of orthoboric acid, borax, kernite, bauxite, cryolite, etc. Fine. And aluminium is the most abundant element and it's the third most abundant element in the earth's crust, which comes after oxygen and silicon. Fine. So aluminium is the most abundant metal, but it's the third most abundant element in the earth's crust, which comes after oxygen and silicon. Fine. So this is about the basics of the boron family. Now talking about the electronic configuration, We know that they have the outer shell electronic configuration, that is ns2, 2 is completely filled, s block is completely filled, s orbital, and np, it will vary from 1 to 6. In case of boron family, it's np1, right? That is what is shown here. And boron and aluminium have noble gas core. Noble gas core is basically ns and np, right? So boron and aluminium both have ns2 and np1 to what 1, fine. So that is they have noble gas core. And in case of gallium and indium, they have noble gas, that is ns and np, plus d10 electrons. They have d orbital as well. Yes, we discussed about that. And thallium has noble gas plus 14f electrons and plus 10 d cores as well. Yes, we saw that also. Thallium not only has ns and np, that is the noble gas core, it also has d orbitals and f orbitals involved as well, right? So this is about the electronic configuration of the elements of boron family. Fine. Moving ahead, the difference in the electronic structure affects the other properties. Yes, right? Because of the difference in the structure differs because of the involvement of d orbitals, f orbitals, right? As we go down the group, and it affects the properties as well, even the chemical properties as well. Fine. And atomic radii, yes, so deviation, that is atomic radii of gallium is less than that of aluminium. So when we talk about the atomic radii of the elements of boron family, there's a lot of deviation involved in it. Fine. So in case of gallium, the atomic radii is less than that of aluminium. Why? We know the answer already, right? Because aluminium has ns and np core, right? Gallium has d orbitals involved. So there's screening effect around involved in this, right? Because the effective nuclear charge and the screening effect, right? So because of that, gallium will have a lesser size. Fine. Because the orbitals because of the d orbitals, the outermost electrons don't experience the effective nuclear charge. It's not that strong, hence the size will be small. Fine. And the variation in the inner core of the electronic configuration, yes, d orbitals, f orbitals, and the presence of additional 10d electrons offer only poor screening effect for the outer electrons from the increased nuclear charge in gallium. Yes, and consequently the atomic radius of gallium is 135 picometer, which is less than that of aluminium, which is 143 picometer. Fine. The reason is simple, because of the involvement of the d orbitals and the screening effect. Next we'll discuss about the ionization enthalpy. Fine. The first one, there is a decrease in the ionization enthalpy from boron to aluminium. Fine. This is because of the size between the boron and aluminium. Boron will have slightly lesser size than aluminium, which is a quite larger size, and hence there is a decrease in the electronegativity. Fine. But then there comes a discontinuity. So there is a discontinuity when we talk about ionization enthalpy between aluminium and gallium, and also between indium and thallium. This is due to the low screening effect, since d orbitals and f orbitals are involved. Fine. And the trend in the ionization enthalpy is the first ionization enthalpy is lesser than the second ionization enthalpy, which is lesser than the third ionization enthalpy. Fine. And the first ionization enthalpies for each of the elements is very high. Fine. So the trend is from boron to aluminium, the ionization enthalpy decreases, and then there is discontinuity because of the low screening effect. Fine. And next, electronegativity. So down the group, electronegativity first decreases. The same thing from boron to aluminium because of the size, and then it increases marginally. Fine. This is all about the electronic configuration, atomic radii, the ionization enthalpy, and the electronegativity. So moving ahead, physical properties of boron family. Fine. Boron is non-metallic in nature. That we discussed by now, right? Boron is non-metallic. All others are all metallic. Fine. And boron is extremely hard and black colored solid. You can see that in the image. It's very hard, and it's a solid which is black in color. And it exists in many allotropic forms as well. Fine. And it has a very strong crystalline lattice, and hence it has high melting point. So boron has lattice of this form. They are all covalently bonded, and it's very strong. Fine. It's a crystalline lattice, and hence it has high melting point. It doesn't melt easily. Fine. And rest of the members are all soft metals. They have low melting point and high electrical conductivity. Fine. Boron is a non-metal, and it has the strong crystalline lattice and high melting point. It's a black colored solid and exists in many allotropic form. But rest all metals, they are soft metals. Rest all elements, fine, and they have low melting point and have good electrical conductivity, fine. And gallium has unusually low melting point and it could exist in liquid states during summer, fine. This is something interesting, and its high boiling point makes it useful material for measuring high temperature, fine. And density of the elements increases down the group as we go from boron to thallium, the density increases, fine. This is all about the physical properties of the boron family. We can see boron is having a little bit exception, right, when compared to other elements. And next up, chemical properties. First, we'll discuss about the oxidation state and the trends in the chemical reactivity. Fine. So, boron forms covalent compound. Why is it so? In case of boron, it is a small size, right? And it has high ionization enthalpy and high electronegativity. And because of this, the small size and all these properties, it cannot form +3 oxidation state, that is +3 ions. And hence it forces boron to form covalent compounds. And hence boron doesn't have oxidation state, like it cannot form +3 ions. But in case of aluminium, aluminium forms +3 ions, fine. And in case of gallium, indium, thallium, they form +1 and +3 oxidation states, fine. And the relative stability of the +1 oxidation state increases for higher elements. That is, as we go down the group, the stability of the +1 oxidation state is more, fine. So thallium has more stable +1 oxidation state than aluminium and so on, fine. And the compounds in +1 oxidation state are more ionic when you compare to the compounds having +3 oxidation states, fine. And in trivalent state, that is nothing but +3 oxidation state, the number of electrons around the central atom in a molecule of the compound of these elements. So when these elements form compounds having +3 oxidation state, the number of electrons around the central atom of these compounds will have only will be only 6, fine. Such electron deficient molecules, they behave as Lewis acids, fine. For example, BF3. And the tendency to behave as Lewis acid decreases as we go down the group. That is, as we go down the group, the size increases, right? So the tendency to behave as Lewis acid decreases as the size increases, fine. So this is about the oxidation states. And in trivalent state, most of the compounds being covalent are hydrolyzed in water, fine. In trivalent state, that is +3 oxidation state, most of the compounds which are covalent are basically hydrolyzed in water. And in this case, yeah, when we were discussing about Lewis acids and all, we can see that BCl3, when it reacts with NH3, that is ammonia, it forms a tetrahedral complex, right? And that is what we discussed when we were talking about the electron deficient molecules behaving as Lewis acid, fine. And aluminum trichloride achieves stability by forming a dimer. So what happens in dimer is, see, when it forms just, there is no stability for AlCl3, right? It is not completely filled. So what happens is it forms a dimer where two chlorine atoms are bridging between two aluminum, and hence it gets a stable configuration, fine. And it still has tetrahedral geometry, fine. This is about the oxidation state and trends in chemical reactivity, fine. Next, we'll discuss about reactivity towards air. So whenever we discuss about chemical properties, we usually discuss about reactivity towards air, that is oxygen, then reactivity with water, and then with halogens. These three are very basic, so you'll have to remember these three, fine. So, reactivity towards air. Boron is unreactive in the crystalline form, fine. And aluminium, it forms a very thin oxide layer on the surface which protects it from further attack, fine. So, when we talk about reactivity towards air, the first element, boron, doesn't react at all. Aluminium, it forms an oxide, layer of oxide on its surface, and hence it will be protected from the attack by when it reacts with air, etc. Fine. And boron, boron, when it is heated in the presence of air, it forms B2O3, fine. Then aluminium, when it is heated in the presence of air, it forms Al2O3. So they are forming oxides in the presence of air, fine. And with dinitrogen at high temperature, they form nitrides, fine. So in presence of air at quite high temperature, they form oxides and nitrides, fine. And The nature of these oxides vary down the group. Fine, we know that down the group there is some abrupt in the properties as well, right? So the nature of this oxide, it varies down the group. And boron trioxide, that is nothing but B2O3, is acidic and it reacts with basic metal oxide. Fine. So this B2O3, boron trioxide, is acidic and hence it reacts with basic metal oxide, metallic oxide, and it forms metal borates. Fine. And aluminium and gallium oxide are amphoteric, and those of indium and thallium are basic in nature. So when we talk about all the elements, boron dioxides are acidic in nature. When we talk about the next two, that is aluminium and gallium, they are amphoteric, and indium and thallium are basic in properties. Next is the reactivity towards acids and alkalis. We'll see how all these elements react towards acids and alkalis. Fine. The first one, boron does not react with acids and alkalis even at moderate temperature. So now we know that boron is unreactive with air in the crystalline form, and it does not react with acids and alkalis even at moderate temperature as well. Fine. And amphoteric oxide, like oxides of amphoteric metals are also amphoteric. In case of aluminium and gallium, we saw they are amphoteric oxides, right? So the oxides of amphoteric metals are also amphoteric. So that we can see in these equations, wherein aluminium trioxide reacts with HCl to give aluminium chloride, trichloride, fine. And then further reactions we yield sodium tetrahydroxyaluminate. So this is about the reactivity towards acids and alkalis. Next is the reactivity with halogens. Fine. So when these elements react with dihalides, they form trihalides of these elements. Fine. For example, when they react with F2, Cl2, Br2, etc., they form like BF3, AlCl3. Fine. This is about the reactivity with halogens. Next, trends and anomalous properties of boron. Now we just realized, right, in every each and every property we saw that boron is having characteristic different properties, right? So we'll talk about those anomalous properties of boron and we'll discuss about the trends as well. Fine. The trichlorides, bromides and iodides of these elements, that is what we discuss now, right? Reactivity with halogens, it forms trichlorides, tribromides, triiodides of the respective elements. They are being covalent in nature and they are hydrolyzed in water. Fine. And the tetrahedral and octahedral species, except in case of boron, they all exist in aqueous medium. Fine. And the monomeric trihalides, that is BF3, etc., they're being electron deficient and they are strong Lewis acids. Fine. The monomeric trihalides like BF3, AlCl3, it's a Lewis acid, right? They're all electron deficient. Fine. And boron trifluoride easily reacts with Lewis bases such as ammonia to complete octet around the boron. We saw that reaction as well. BF3 reacting with NH3 to form a tetrahedral geometry, right? And yeah, that is what is shown here. They complete the octet around boron while reacting with ammonia. Fine. And the maximum covalency of boron is 4. Yes, because boron has Ns and Np orbitals involved in it. So 1 s orbital, 3 p orbital. So the maximum covalency is 4. Fine. And this is due to the absence of d orbital. But the other elements, the covalency can exceed beyond 4 because they have the presence of d orbitals and f orbitals involved in them. Fine. And most of the other metal halides, that is Al3L3, are all dispersed through halogen bridging. Fine. So yeah, we saw it in case of AlCl3, right? 2 aluminum atoms are bridged by 2 choline atoms, right? And that is what Al2Cl6. The octet is complete. They are stable because of the bridging of the halogen atoms. Fine. And the metal species completes its octet by accepting electrons from halogens in the halogen bridge molecule. That's the same thing. It attains stability, that is, it gains octet by accepting the electrons by these bridged halogen molecules. Fine. Next up, yeah, this is how the aluminium. This is nothing but Al2. The blue color atoms are nothing but aluminium, and the green ones are nothing but chlorine. This is a molecule, that is the compound Al2Cl6. Fine. Next, some important compounds of boron. The few important compounds of boron are borax, orthoboric acid, and diborane. So we'll discuss about all of these now. Fine. So first up, borax. Borax looks something like this, and it has the formula Na2B4O5 OH 4 times into 8H2O. Fine. The structure looks something like this. Fine. And it's a white crystalline solid, and borax dissolves in water to give an alkaline solution. Fine. And this is the reaction to get orthoboric acid. Fine. That is the same thing. It reacts with water to give an alkaline solution, that is NaOH, and it gives orthoboric acid. Fine. And the same thing when it is heated, when it is the same thing, that is borax, when it is heated, will give sodium metaborate and boric anhydride, that is B2O3. Fine. And the next one is orthoboric acid. We just saw how orthoboric acid is obtained, right? So this is how orthoboric acid looks like, the structure of orthoboric acid. Again, it is a white crystalline solid. It has a soapy touch. Fine. And it's sparingly soluble in water, and it is highly soluble in hot water. So this orthoboric acid in the regular normal water, at room temperature, it's sparingly soluble, but when the temperature of water is increased, that is for hot water, it is highly soluble. Fine. And next, boric acid is a weak monobasic acid. Fine. And it is not a protonic acid. Fine. It is not a protonic acid, but it acts as a Lewis acid by accepting electrons from the hydroxyl ion. Fine. This boric acid is a weak monobasic acid, but it's not a protic acid, but it still reacts as a Lewis acid by accepting electrons from an hydroxyl ion. Fine. And this is the reaction when boric acid at considerably high temperature forms metaboric acid, and then we get the boron trioxide, like the previous equation itself. Fine. And next, diborane. How diborane is obtained is BF3, that is boron trifluoride molecules. It reacts with lithium aluminium hydride, and we get a compound that is diborane. Fine. So this is how diborane looks like, and again over here there is a bridging of hydrogens between two boron atoms, right? And to be more clear, this is how it looks like when the orbitals are involved. Fine. And this is the three-dimensional image of diborane. We can easily see that each boron is attached to two hydrogen each, fine, separately, and there are two hydrogens above the plane and below the plane, and they are bridging between two boron atoms, right? That's the same thing. There are four terminal hydrogen atoms. Terminal are on the either sides of boron, fine, and there are four terminal hydrogen atom and two boron atoms. All these lie on the same plane. That is the two boron atoms and four terminal hydrogen. All of them lie on the same plane. And above the plane there is one hydrogen, and below the plane there is one more hydrogen. These act as bridging hydrogen atoms. Fine. And the four terminal BH bonds are regular two-centered two-electron bonds. Fine. While two bridged bonds are different. Fine. Those four terminal BH bonds are regular two-centered two-electron bonds, while the bridged bonds are different. Fine. And the reaction of ammonia with diborane gives something known as borazine. Fine, this is something interesting. So when ammonia reacts with diborane, it forms something known as borazine, and it is known as inorganic benzene. And this is how it looks like. It looks more or less like benzene structure, right? It's a six-membered ring, and hence we call it inorganic benzene. Fine. And boron also forms a series of hydroborates. Fine. This boron not only forms all these and not only inorganic benzene, that is borazine, it also forms a series of hydridoborates. Fine. And lithium and sodium tetrahydridoborates are also known as borohydrides. Fine. And they are prepared by the reaction of metal hydrides with B2H6. B2H6 is nothing but diborane, right? In diethyl ether. So when diborane reacts with metal hydrides in diethyl ether, we get something known as hydridoborates. And lithium and sodium tetrahydridoborates are also known as borohydrides. Fine. So now we'll discuss about the uses of boron and aluminium. Boron is extremely hard solid. We discussed it, right? It's extremely hard, it's black, it has high melting point, it's covalent, etc. etc. It has low density and very low electrical conductivity. Yes. And boron fibers when we talk about the uses of boron, it's used as boron fibers, which are bulletproof vest, and they're used in bulletproof vest and light composite material for aircraft. So this is the use of boron fibers. And the boron 10 isotope, we discussed that boron has two isotopes, right? Boron 10 and boron 11. The boron 10 isotope has high ability to absorb neutrons, and therefore metal borides are used in nuclear industry as protective shields and control rods. Yes, when we talk about nuclear reactors and all, we know that boron is used as control rods in nuclear reactors, right? And this is the reason for it, because boron 10 isotopes has high ability to absorb neutrons. Fine. And next, when we talk about borax and boric acids, they're used in the manufacture of heat resistant glasses, glass wool and fiberglass. Fine. And borax is used as flux for soldering metals. So when people use soldering and all, right, in that case borax is used in the case of flux. And it's used as flux for soldering metals, for heat, scratch and stain resistant glass coating to earthenwares, and as a constituent of medicinal soaps as well. So borax is used as a constituent of medicinal soaps also. And an aqueous solution of orthoboric acid is generally used as mild antiseptic. So we can see the use of borax in medicinal field also. It's used in medicinal soap, and an aqueous solution of orthoboric acid is generally used as mild antiseptic. So these are the uses of boron. Fine. Now moving ahead, aluminium. Aluminium is a bright silvery white metal, and it has high tensile strength, high electrical and thermal conductivity. Yes, and the electrical conductivity aluminium is twice as that of copper. When we check it by weight, usually we know copper is very good conductor of heat and electricity, right? But when we compare it with aluminium in terms of weight, it has high electrical conductivity when it compared to copper. Fine. And aluminium forms alloys with copper, manganese, magnesium, silicon and zinc as well. Fine. And it is used in the packing, utensil making, it's used in constructing aeroplanes and transportation industries as well. So these are all some very good applications of aluminium. The first one is it has good electrical conductivity, and it forms alloys with copper, manganese, magnesium, silicon, zinc, etc. And it's used in packing, utensils, construction of airplanes, construction, airplanes and transportation industries. Fine. And the use of aluminium and its compounds for domestic purpose is now reduced because they are considering it as toxic. Fine. Since aluminium is toxic in nature, they have reduced the use of aluminium in domestic purposes. Fine. So this is all about the boron family. So now we discussed about all the elements of the boron family, their physical properties, chemical properties, and the trends, their uses, the special compounds of boron, aluminium, etc., and the anomalous behavior of boron, etc. So now we have a better idea about the boron family, that is the group 13 elements. Moving ahead, now we'll discuss about carbon family. And thank you for watching. If you are liking this course, please don't forget to like, share and subscribe to read my course. Thank you.